Define Helmholtz free energy to be U minus St. The infinitesimal change of Helmholtz free energy is calculated with the infinitesimal change of internal energy and the product rule in calculus. Define the Gibbs free energy to be H minus St. The infinitesimal change of Gibbs free energy is calculated with the infinitesimal change of enthalpy and the product rule in calculus. The change of Gibbs free energy has special chemical significance. First, according to the infinitesimal form of Gibbs free energy, the partial derivative of Gibbs free energy with respect to pressure with temperature held constant is volume. Therefore, the change of Gibbs free energy due to the change of pressure in an isothermal process can be calculated by integrating VdP from the initial pressure to the final pressure. For liquids and solids, the volumes do not change with pressure significantly. Thus, the integral becomes V delta P. For ideal gases, the volume can be substituted using the ideal gas law. Since temperature is a constant, the change of Gibbs free energy is in the following form. Let's have a look at the free expansion, where the final volume is twice of the initial volume, so the final pressure is half of the initial pressure. The Gibbs free energy change can be calculated using an isothermal process, similar to what we did when we calculated the entropy change. Another example is the compression of water. You can find that, although the pressure change of the condensed matter is much greater, the Gibbs free energy change of the gas is much more significant. We can conclude that the Gibbs free energies of condensed matters do not change with pressure significantly. On the other hand, according to the infinitesimal form of Gibbs free energy, the partial derivative of Gibbs free energy with respect to temperature with pressure held constant is the opposite of entropy. The entropy change in an reversible isobaric process can be calculated by integrating entropy with respect to temperature from initial temperature to final temperature. Unfortunately, the entropy of the system is usually difficult to find. In such case, we can use Gibbs Helmholtz equation. It is the relation between the change of Gibbs free energy and the enthalpy. Please pause to check the simple derivation by yourself. The relation between Gibbs free energies at different temperatures but constant pressure can be calculated by integrating the Gibbs Helmholtz equation. This is the precise way to evaluate Gibbs free energy at a temperature where the thermodynamic data are not provided. In a general chemical reaction, the reaction Gibbs free energy can be calculated from the Gibbs free energies of the reactants and products, similar to what we did for reaction enthalpy and reaction entropy. Divide the equation by temperature and differentiate it with respect to temperature with pressure held constant. The term of each reactant and product can be replaced by Gibbs Helmholtz equation. Then we have got another form of Gibbs Helmholtz equation. By integrating this Gibbs Helmholtz equation, we can evaluate Gibbs free energy of reaction at any temperature, if we know the Gibbs free energy of reaction at some temperature and the reaction enthalpy. On the other hand, the molar Gibbs free energy of each reactant and product can be expressed with enthalpy, entropy, and temperature, as it is defined. Then we find that the reaction Gibbs free energy is reaction enthalpy minus temperature multiplied by reaction entropy. In principle, both reaction enthalpy and reaction entropy are temperature dependent. Let's see how we can simplify the calculation. Suppose that the reaction enthalpy and the reaction entropy are provided at T', but the reaction Gibbs free energy at T is concerned. Also suppose that the heat capacity change of the reaction is temperature independent. Thus, the reaction Gibbs free energy can be expressed with the following equation. Suppose the difference between T and T', delta T, is much smaller than T'. Then, the term in logarithm can be expanded with Taylor series. Here, since delta T is small, we only keep the first order. Bring it back to the expression of reaction of Gibbs free energy, and use the presumption that T is close to T'. We surprisingly find that the reaction Gibbs free energy at T can be calculated with reaction enthalpy and reaction entropy at T'. It is because the change of reaction enthalpy and reaction entropy with temperature cancel each other to a large extent. Here, we have an example of the fusion of water. The enthalpy and entropy of fusion of water are provided at 0 degrees Celsius. The Gibbs free energy of fusion of water can be calculated directly with them. Pay attention to the signs of Gibbs free energy above and below 0 degrees Celsius. We will recall them later. On the other hand, the heat capacity change in the fusion of water is also known. With it, the enthalpy of the fusion of water as a function of temperature can be calculated. Then, we can use the Gibbs Helmholtz equation to calculate the Gibbs free energy of fusion of water at 283 Kelvin. Note that this result is accurate. We can find that this accurate value is only slightly different from the approximate calculation in the previous slide. Now, consider a process of a closed system. The system and its surroundings are both at temperature T and pressure P. The entropy change of the system in the process is ds. The heat of the system in the process is delta Q. Pay attention, ds is not necessarily delta Q divided by T, because the process is not necessarily reversible. On the other hand, the process of the surroundings is reversible. Thus, the entropy change of the surroundings is minus delta Q divided by T. Since the process is isobaric, the heat is equal to the enthalpy change. The entropy change of the universe is the sum of the entropy changes of the system and the surroundings. It ends up with the Gibbs free energy change divided by temperature. Obviously, the sign of the entropy change of the universe is opposite to that of the Gibbs free energy change of the system. We also know from Planck's statement of the second law of thermodynamics that the entropy of the universe, which is an isolated system, always increases. So, we have the conclusion that a process at constant temperature and pressure of a closed system is spontaneous if its Gibbs free energy decreases. For example, at 263 Kelvin, the Gibbs free energy of fusion of water is positive. So, the melting of ice at 263 Kelvin is non-spontaneous. At 283 Kelvin, the Gibbs free energy of fusion of water is negative. So, the melting of ice at 283 Kelvin is spontaneous. We can easily reach a similar conclusion. A process at constant temperature and volume of a closed system is spontaneous if its Helmholtz free energy decreases. In a chemical reaction, if the enthalpy decreases and entropy increases, the Gibbs free energy always decreases. Such reaction is spontaneous at any temperature. A typical example is the decomposition of hydrogen peroxide to water and oxygen. If the enthalpy increases and entropy decreases, the Gibbs free energy always increases. Such reaction is always non-spontaneous. A typical example is the reduction of sodium oxide by hydrogen. If the reaction enthalpy and reaction entropy have the same sign, the reaction has an equilibrium temperature where the reaction Gibbs free energy is zero. Most reactions belong to this type. If both enthalpy and entropy increase, the reaction is spontaneous at a higher temperature. For example, the decomposition of water. If both enthalpy and entropy decrease, the reaction is spontaneous at lower temperature. For example, the formation of silicon dioxide. Like standard enthalpy of reaction and standard entropy of reaction, we can define the standard Gibbs free energy of reaction. It is the molar Gibbs free energy change in the system during a chemical reaction, when all the reactants and products are in their standard states. We can also define the standard Gibbs free energy of formation, like standard enthalpy of formation. It is the Gibbs free energy change during the formation of per mole of substance from its constituent elements, with all the substance in their standard states. The standard Gibbs free energy of reaction can be calculated from the standard Gibbs free energy of formation of the reactants and products. The logic behind the calculation is the same as the calculation of standard enthalpy of reaction. Pay attention, standard Gibbs free energy of reaction is temperature dependent. The data books only provide standard Gibbs free energy of formation at certain temperatures. At a different temperature, standard Gibbs free energy can be calculated by Gibbs Helmholtz equation. Alternatively, the standard Gibbs free energy of reaction at any temperature can be calculated from the standard enthalpy of reaction and standard entropy of reaction at that temperature. At a temperature T near the temperature T' where thermodynamic data are provided, standard Gibbs free energy of reaction can be approximated by the given standard enthalpy of reaction and standard entropy of reaction. Let's use the reaction of graphite and oxygen to form carbon dioxide as an example. The data are provided at 298 Kelvin. The standard Gibbs free energy of reaction is equal to the standard Gibbs free energy of formation of carbon dioxide, because graphite and oxygen are elements. The standard Gibbs free energy of reaction can also be calculated from the standard enthalpy of reaction and the standard entropy of reaction. The standard enthalpy of reaction is equal to the standard enthalpy of formation of carbon dioxide, because graphite and oxygen are elements. The standard entropy of reaction is the difference in standard molar entropies of the products and reactants. The results are the same because we use the same temperature for calculation.